Hi everyone, I'm Inchi. I'm a PhD student from University of Illinois at Urbana-Champaign and advised by Professor Paolo Gardoni. This video is about the work I've been recently working in collaborating with Dr. Nitesh Sharma. The topic is validating the current state of practice for risk and resilience analysis. Risk and resilience analysis assists decision making on natural hazard for governing bodies, planning authorities, utility companies, and insurance companies. Hazard impact models are often foundational for assessing infrastructure functionality, economic loss, and societal impact in subsequent analysis. Multiple models for risk and resilience analysis are available and widely used in academia and practice for their simplicity and computational efficiency. However, due to limited validation data, the models for risk and resilience analysis are often not rigorously validated. Past studies have examined such models for different hazard types. However, there consistently remains a lack of literature validating hazard prediction models. Limited studies have validated the predictive estimates by using real-world post-earthquake data, and there's a lack of valuable validation for damage models related to buildings and infrastructure like power, water, and transportation. And there's a lack of available measurements for validation. To overcome the limitations, we propose three accuracy measures for validating the model prediction of hazard intensity measures, building damage, and infrastructure damage. So the following presentation, I'll introduce the three measures of accuracy we propose in this work and show the proposed measurement and implication by using the seismic hazard as an example. And in the example, we'll show the validation of hazard intensity predictions, building damage, and infrastructure damage, and we will wrap up with summary and future work. As the first measure to compare models, we propose the accuracy likelihood to quantify the overall precision of the model. The accuracy likelihood is defined as the likelihood of the model accurately predicting recorded damage. So for each physical structure, we extract the estimated likelihood for the recorded damage state from the model. We then sum up all the likelihood after applying a logarithm transformation. A smaller value indicates higher accuracy for the model. For example, the figure below shows the likelihood output for the damage state of a building. So if the recorded damage state is extreme, which is the orange color in this figure, we can take the likelihood for the recorded damage state, which is equal to zero point 0.3, as the model's accuracy likelihood. And the total accuracy likelihood can be calculated after a logarithm transformation. So we can apply the first measure when the model's output is likelihood prediction, and when the prediction object of interest can be assumed to be dependent. This measure enables straightforward accuracy comparison based on likelihood values. However, it does not quantify the deviation between the predicted and the recorded values. In the second measure, we propose the prediction error to assess the degree of deviation between the predicted and recorded values. Analyzing the pattern of prediction error helps identify bias where the model tends to under or overpredict. So we use the absolute error to measure the discrete value result and use the relative error to compare the continuous value result. A lower prediction error indicates a more accurate model. So for example, the figure below shows the likelihood output for the damage state of a building. So if the predicted damage state is slight, which is green color in this figure, and if the recorded damage state is extreme, which is orange in this figure, then the absolute error is 2 damage state. We can apply the second measure when models provide either continuous or discrete estimation values. This measure is essential for understanding prediction limitations and identifying areas for improvement. However, it does not consider the underlying data distributions and fails to capture the overall similarity or difference in their distribution characteristic. So in the third measure, we propose the distribution match to assess the degree of resemblance or dissimilarity between the predicted and recorded distribution. So the two distributions are likely from the same underlying population if there are no significant difference suggested between them. We can apply statistical tests to analyze the shape, central tendency, spread, and other characteristics of the distribution. For example, the figure below again shows the likely output for the damaged alpha buildings. So we have the predicted likelihood distributions and also the recorded likelihood distribution. We can use Kullback-Leibler divergence to compare the overall dissimilarity between the two distributions. We can apply the third measure when the model provides prediction of likelihood distribution and when there's enough simple data to estimate the distribution. So this measure provides a comprehensive understanding by assessing the overall similarity or difference between the distributions. However, this measure does not provide a detailed understanding of individual prediction results. Since the three measurements provide us with different information, so we apply all three measures in the application. We choose seismic hazard as an example to show the proposed measure of accuracy. The earthquake under consideration is the main shock of the 2016 Kumamoto earthquake in Japan, and the major damage was in Mashiki City, which is near the epicenter. We then select hazards and maybes to test their prediction accuracy. And to be noted that the proposed measures are applicable to different models. For example, we also validate the prediction model proposed in the Kumamoto disaster plan, but considering the length of this presentation, we will not put the material here. We collect and create the damage data in Mashiki City, and the data include the building information, bridge inventory, potable water and wastewater infrastructure data, and the electrical power infrastructure in the entire Kumamoto area that includes Mashiki City. For hazard intensity, we use the GNPs developed by Borat all in 2014 to predict the hazard intensity measures. So we can find that the predicted intensity are mostly lower than the recorded values. And since the prediction does not provide likelihood estimation, we cannot apply the second measure, which is prediction error, for validation. We apply the relative error in terms of the percentage difference between the median predicted and the recorded values. The predicted PG and SA are mostly 100% lower than the recorded data, and the predicted TGV are comparably more accurate than the others. The predictions are more accurate when the location is closer to the epicenter, and less accurate when the epicenter distance is larger than 600 kilometers. And due to this inaccurate prediction result, we use the predicted and recorded hazard intensity separately as the basis for the following damage prediction, which means that we compare the two sets of results. One is the predicted damage by using the predicted hazard, and the other is the predicted damage and using the recorded hazard. For building damage validation, the prediction output, which is a likelihood prediction, allows us to apply all three measurements. So the figure from right to left are the recorded actual damage and the predicted damage by using the predicted hazard of hazards and maybes, and on the right is the predicted damage and using the recorded hazard. So to apply the first measurement, which is the accuracy likelihood, we take the accurate likelihood for each building within the area and sum their logarithm values to obtain the total accuracy likelihood. And the result is shown in the table. So hazards predicted damage more accurately than maybes in both the predicted and recorded hazard scenarios, and using recorded hazard as a basis for damage prediction lead to lower accuracy. To apply the second measure, which is prediction error, we use the absolute error to measure the distance between the predicted and recorded damage state. So the figure on the right is the error of predicted damage by using the predicted hazard, and on the right is the error of predicted damage by using the recorded hazard. So the absolute error shown in the confusion matrix indicate that hazards tend to underestimate the damage, while navies generally overestimate the damage. To apply the third measurement, which is distribution match, we compare the likelihood distribution between the predicted and recorded result. And HAZAS has a more similar distribution shape to the recorded values for the building structural type W1 and W2. So for bridge damage validation, we just did the same procedure to the data. So we can find that in the accuracy likelihood measurement, HAZA still predicted damage more accurately in both the predicted and recorded HAZA scenarios, and using recorded HAZA as a basis still leads to lower accuracy. And in prediction error measurement, HAZAS has a more accurate prediction in the case of no damage, but it also shows larger prediction errors. So recalibrating the model for navies will be more visible and likely to result in increased accuracy. And in the distribution match measurement, HAZAS has a distribution shape that is more similar to recorded values compared to navies. So we also did a similar measure to the potable water infrastructure. And in the accuracy likelihood measure, HAZAS and navies have similar accuracy, and using recorded hazard as a basis still leads to lower accuracy. And in this prediction error measurement, the confusion metrics indicate that both models have similar prediction error and only one demonstrates off compared to the recorded data. In the distribution match measurement, HAZAS has a distribution shape that is more similar to the recorded values compared to navies. And the same measure to the wastewater infrastructure. However, due to the limited number of data points that we only have one wastewater treatment plant within the area, so we're unable to conduct the distribution match measurement. So in the accuracy likelihood measure, HAZAS and navies have similar accuracy, and using recorded hazard as the basis still leads to lower accuracy. And in prediction error measurement, both models have similar prediction errors, and only one demonstrates off compared to the recorded data. For electrical power infrastructure damage validation, in the accuracy likelihood measure, Mavis has better performance than HAZAS, and using recorded hazard as a basis still leads to lower accuracy. And in the prediction error measurement, both HAZAS and navies predict the electrical substation damage relatively well. However, HAZAS has a larger and more inconsistent prediction error compared to navies. So recalibrating the model for navies would be again more feasible and likely to result in increased accuracy. And in the distribution match measurement, HAZAS and navies have similar distribution that are slightly different from the recorded values. So to sum up, this work proposed three accuracy measures for validating the hazard impact analysis that serves as foundational elements for other subsequent research. And in our example, the results show that both hazards and navies tend to underestimate the hazard intensity and overestimate the damage. The performance is better for infrastructure components and buildings, which we attribute to the higher standardization and uniformity present in infrastructure components compared to buildings. So it is important to be aware of the errors associated with the models we use as a foundation for the subsequent research. So in the future work, with the complete data set we created, ongoing work is extending the validation to other damage prediction models. And the next step of this work involves validating the predictive models for recovery, economic loss, resilience, and network functionality. In addition to validation, ongoing work will focus on developing a Bayesian approach to update the model parameter as the new data becomes available. So this is all I have for today. If you have any question, you can contact me via my email. And welcome to check on our group's Twitter and YouTube channel to find more interesting work. Thank you.